Hello, everyone. Thanks for making it to the last session. Hopefully, it's going to be worth it. So I'm Andrea Mambretti from IBM Research, and today I'm going to present you our systematization of knowledge on automated exploit generation for the kernel. I'm here on behalf of my colleagues Anil and Alessandro from IBM, and Vincent, Damian, and Bernhard from armasuisse. So before going into the details of what we did in our systematization of knowledge paper, basically, let's have a look at automatization of attacks, a little bit the story. And let's start from 2009, when Sean Heelan published his master thesis on, and this was the first sort of attempt to try to automatize attacks, in particular control flow hijacking. Just a few years later, in 2011, we have Avgerinos that basically brought this to the next level and introduced automatic exploit generation, the term that we use today. And Avgerinos basically tried to automatize all the steps, not only the control flow hijack, but basically getting to a final exploit and get basically privileged escalation. All this work, of course, focused on basically exploitation in regular programs, so not yet into the kernel. Afterwards, if we fast forward a few years, we have in 2016 the end of the CGCs, the DARPA Cyber Grand Challenge, where several teams were invited to basically participate and develop cyber reasoning systems that were playing attack and defense CTFs. And this was a turning point in terms of development in automated exploit generation. Basically, the Cyber Grand Challenge gave a huge push towards this field, and we have seen as an outcome considerable advances in static and dynamic techniques, as well as we got out of this competition several tools that were already existing before, but they were heavily developed during the competition, and they became mature to basically do this type of analysis. However, of course, the CGC was a limited time constraint competition, so that the organizer decided to provide a simplified operating system and architecture for the competitors to compete with. And in fact, the operating system had only 7 system calls, and that's quite far from modern operating systems, right? Also, of course, the focus was on exploitation on regular applications, local applications, and so these applications were quite small in size, very small, and it was only focusing on binary code. And the attackers were not really completing the exploit, but they had to provide a proof of vulnerability, which meant just showing that, for instance, they could control the instruction pointer. So we had 10 years. It's been almost 10 years now from the end of this competition to basically bring all these techniques and bring the overall field to the next level. And in our SoK, we focused on all this work that tried to attack basically one of the ultimate targets, the kernel. The kernel is very important because, of course, it's a high privilege. If you can compromise the kernel, you can take down the system. It's interesting because it has a very large attack surface, right? And you can think about many ways where you can attack the kernel. It's not just one single scenario. And of course, most of the work that we looked at, they look at Linux. And Linux, as we know, is widely available and used everywhere from our phones, embedded systems, servers, and so on. Of course, there are challenges of taking Linux. These days, I think we reached almost 40 million lines of code, so it's a beast. There are several threat models, as I was mentioning, that should be considered. And Linux, of course, as every kernel, offers a specific type of attacks that are valid only within the context of Linux. And as well as there are several mitigations that are available that we need to model if we want to build attacks that are actually working in a modern system. So the threat models that we identified during our systematization of knowledge are the following. We have the usual local and remote attackers, but we also have now these days containers, user sandbox like eBPF, basically the normal user sandbox, but we also have like kernel sandbox where, for instance, the attacker is sitting in an eBPF program and he might want to try to escape from the eBPF sandbox. We have also situations like when system is running purely in lockdown, and so we have like a root user that is trying to access the functionality that are not available in lockdown mode and so on. In our systematization of knowledge, we also introduced a new taxonomy that is specifically looking at attacks and vulnerabilities within the kernel. That is trying to fill the gap compared to the available taxonomy. And we identified 3 different groups of vulnerabilities that are generally take part in a full exploit within Linux. We have what we call precursor vulnerabilities. These are vulnerabilities that without another vulnerability, they will not basically bring any serious consequences. And for instance, generally, if we think about an integer overflow, it's generally paired to something like an out-of-bound write, and without the presence of an out-of-bound write, generally an integer overflow does not really do much. We have also helper category of vulnerabilities. These vulnerabilities tend to be vulnerabilities that they have a serious impact, but they might not directly help the attacker they basically help the attacker to reach their goals, only paired with another vulnerability. One example, for instance, is if we want to perform a privilege escalation and there is a KSLR in the kernel deployed, we might need to have like an information leakage to pair to our basically out-of-bound write to basically perform the exploit. And then we have finally the base category, and this is all the vulnerabilities available in the kernel that allow an attacker to reach their goal directly. So let's have a look at an example of how we can apply this taxonomy to a real vulnerability. I took this CVE out of like Google Project Zero blog post. This is from Jan Horn. And I took this example because this example is a quite complicated POC, and it requires like a lot of like techniques and a lot of bugs to be exploited. So we have 2 threads. We have on one side like a regular thread that is controlled by the attacker, and then we have like the garbage collector for Unix socket domains within the kernel. So we start with like some initialization, so the attacker can initialize some SKB, so socket buffers in the kernel, and these objects are very complex objects, but they do have like a file descriptor and a reference count. The reference count is basically just used to keep track if there are elements in the kernel that hold on like a reference to this object. And they are used by the garbage collector to figure out if the garbage collector is the only one holding the final reference, and so the garbage collector can go and free the object because it's not used anymore. However, here basically, as you can see from the garbage collector side, we have the check, and the check is basically saying, okay, am I the only one having the reference? Yes. If that's so, the garbage collector can treat the object as is the only one having the reference, so can go and operate on this object. And the garbage collector, of course, is going to go and free something. But on the other side, we have this acquire file descriptor. This is a high-level function that I defined. It's a bit more complicated than this, but you have to imagine that there is basically the possibility for an attacker to acquire the file descriptor, and before incrementing the counter, so notifying everyone else that, oh, I have this file descriptor with me, there are 12 instructions. So it's a tiny window in which if the garbage collector basically performs the checks in between when we get like the file descriptor and then we bump the counter up, the garbage collector will still think that basically he's the only one holding this reference. And in our this basically brings a very small race condition, and in our taxonomy, we call it basically a precursor vulnerability race condition. Here, without anything else, this will be just a very tiny bug that might not lead to anything. However, if you see here, of course, the garbage collector will perform a free, but we also have a use from the attacker side. And this basically can bring a use after free into the game. And we define this as a base memory in time vulnerability. And we refer to it, this is basically the vulnerability that will allow us to perform the privilege escalation. However, this is a very tiny window, right? So for an attacker to exploit this is still very hard. So we foresee, in the real exploit, Jan Horn used 3 different techniques to synchronize the thread in a perfect manner. And using these techniques, we basically define them, like the use of the timers that are available in Linux to pause these threads and synchronize them. We define them as another vulnerability, but this is a helper vulnerability specifically for race conditions. And of course, this was not treated in the original POC, but we foresee that if you want to really complete the exploit and do privilege escalation using this vulnerability, you will need to find a way to, again, bypass KSLR and as well as like mangling the memory. And so here we have like this helper memory in time as well as a helper memory of ASLR within our taxonomy. So in a way, what we try to do with our taxonomy is try to improve the thinking about complex exploits, basically divide them in basic blocks that we can think about that are necessary to perform the exploitation. And in our paper, we basically, when we looked at the working in exploit generation, we mapped them towards our taxonomy, and there is a nice table for that. We also defined the exploitation steps that are necessary to build the automated exploit generation for the kernel. Of course, first step, we need to find a vulnerability. And that's basically involves all the classes vulnerabilities I talked about before. And the second step is, of course, once we found the vulnerability, we need to find a trigger for that vulnerability. While if we apply, for instance, fuzzing, these 2 stages are done at the same time, because fuzzing, when it finds the vulnerability, also gives us an input for that vulnerability. But that's not true, for instance, for static analysis techniques. Then, of course, we need to understand and characterize the vulnerability. What can we do with it? For instance, if we have an out-of-bound write on the heap, we need to figure out how many bytes can we write out of bound. Are these bytes arbitrary, or they are constrained in any way? And we need to understand what kind of capabilities we get. Finally, afterwards, we need to, of course, decide, okay, what the attacker wants to do, and how many of these vulnerabilities we need to piece together to be able to reach that goal. And so we need to build an exploitation strategy. And then there is the final part where we put everything together in a reproducer program or POC program that is triggering the vulnerability. So in our SoK, we applied the taxonomy and the stages to several works that we took from the top-tier venues in the past 10 years, from 2013 to 2023. And then we took also the cited papers from this first selection, and we filtered out for either new techniques for the kernel, so for exploiting the kernel, or specifically any paper that worked on one of these stages of automation towards automated exploit generation. We basically found 41 total papers. 22 were specifically looking at stage number 1, finding the vulnerability, and they were divided in 14 static analysis tools and 8 fuzzing tools specifically for the kernel. We have 9 that look at the remaining stages, so from S3 to S5, on automated exploit generation, and then 10 were actually introducing just new techniques into the kernel. So now, I'm not going to give you the details of all the papers. There are nice tables in our article that I really invite you to go and look, where we map all these papers based on the tools they use and the stages they tackle and so on. What I would like to discuss in the remaining part of my talk is about open problems that we discovered in current research on automated exploit generation for the kernel. The first one is the attack model and goals that were considered in the papers we've seen. Most of the work that we've seen actually was thread model agnostic. And they were the one that instead considered an attacker, always considered a local attacker. But again, as I was showing you earlier, there are many different scenarios in the kernel that should be considered and where the attacker can sit and try to perform exploitation, but that's not generally considered by this work. And also, of course, privilege escalation and information leakage are king. So most of the papers that we have seen, of course, focus on those because they are most prominent. But we also think that denial of service specifically for the kernel is still an important goal for an attacker, can really have a huge impact. And we've seen some CVs come out like in the past 2 or 3 years that were indeed like very serious. So, and this is some shortcoming basically from the research we have seen. Another open problem is the fact that most of the papers were not really looking at assessing the gravity of a certain bug. One of the reasons of doing automated exploit generation from a defense point of view is actually to use this as a motivator to go and fix the bug as soon as possible. So you find a bug, you try to generate an automatic exploit, and then go to the defender and say, okay, like, look, this is actually, we found an exploit, and go and fix it as soon as possible. However, for instance, for all the papers that were doing static analysis, of course, static analysis tell you where the bug is, but that doesn't give you any input, so you cannot really assess, how the gravity of the bug, just basically knowing the location of the bug. If we take instead like dynamic analysis, we have several different situations, right? The first one is like static dynamic analysis not finding the bug because we didn't run it for long enough, but that's okay. I mean, but then let's assume we have a case where we find the bug. So the dynamic analysis is giving us like the input to reach that bug, but the path that we take is actually very constrained. If we run our analysis might tell us, okay, we didn't find an exploit, or we have this exploit, but this is there is very little control from an attacker point of view against this bug, so it's not really a severe bug. However, maybe there is another path to this bug that we did not consider, and that is instead a non-constrained path, so the attacker has full control of this vulnerability, and so there is much more to be done with it. We found that only 2 papers out of the 41 we analyzed were actually considering this scenario where found a bug. They will try to find all possible paths towards this bug to then have a full assessment of the exploitability. Another issue that we've seen is like portability. And here I have an example. So S2E, for whoever did not have the pleasure to work with, is a symbolic execution engine and is widely used for automated exploit generation of the kernel because it allows you to do symbolic execution in the kernel. But of course, to do that, it's a massive tool with a lot of dependencies. And so when you develop something within S2E, if you want to move any of these components to a newer version and so on, there is a lot of engineering that needs to happen that people don't really care about, because of course you care about working on your own analysis, you don't care about moving things. And so, and for instance, S2E is very constrained on which kernel you can run in it. And so your analysis will be focused on one single version of the kernel. If you want to try something different or newer kernels, it's a lot of engineering. And there is, across the board, an issue on portability and flexibility on where using different kernels, different dependencies, and so on. One other issue was reproducibility. Every paper we've seen, they always use their own version of the kernel. They just get a set of bugs that they care about and do the analysis for. And it's very hard to then compare different mechanisms. And people tend to not do it. Just like they just say, okay, this is the kernel we use, these bugs we found, and that's pretty much it. But one thing that we recommend would be to all the research community to just decide, okay, let's settle on a set of bugs that like a data set of bugs that we want to analyze, that we want to try to automatize the exploit for, as well as like one specific version of the kernel. And then we will be able to compare mechanism or different stages altogether. Finally, tool reuse, another open problem. We've seen a good reuse of the tools like SysCaller, LLVM, S2E, and Anger. These are like at the base of all the analysis we've seen. However, we have seen most of the projects were taking these base tools and redeveloping the wheel over and over again. Several different basic functionalities were reinvented all the time. And that's the main issue because, of course, it slows down the progress, as well as like people basically don't really, when they develop a new feature, for instance, for S2E, they don't really go back to S2E and basically contribute to the main line. That they just don't care. They just finish their own projects, get their own paper out, but there is no real cycle in the community. Oftentimes, we've seen also some papers don't providing a code. I mean, 2025 people publish your code. That's very important for the community, even more than the papers. And oftentimes, all these projects have been focusing on the single steps in the pipeline. And it will make sense to say, OK, I take paper A that works on one stage of the pipeline, and I take a paper B working on another stage of the pipeline, and then I use these techniques together. Taking the code from different projects and put them together is a project in its own, and it's super hard because generally there are no APIs defined, and this is a big issue. So it's basically setting back like this whole field quite a bit. So there, one of the recommendations would be to define, write code that is more, use proper engineering and define proper APIs and again, contribute back to the community. So in conclusions of the status of kernel AAG in the past 10 years, so we have not yet seen a full automated exploit generation for the kernel at scale because most of the research, of course, focused on different parts of the pipeline, and there was not really an effort to put everything together yet. Again, there was like some shortcoming in the threat models that we've seen, but this is, let's say, a minor issue. But and the major issue that I see is like a very limited reuse of the state of the art, and it's very hard to take whatever has been done directly because oftentimes, again, the code is brittle or it just works for the cases of the paper. But if you try to do it with something different, then things breaks very quickly. And with this, I conclude. If you have any questions, I will be happy to answer.